Thank you, Dr. Anhari, for a very kind introduction. Thank you all for joining the webinar. I'll be talking about sonic speed photoacoustic tomography, light speed compressed ultrafast photography, and super resolution quantum imaging in the next 30 minutes. Why optics for imaging? Light is very special because we can probe molecules, we can address molecules because the EM spectrum at the optical regime allows us to interact with the molecules directly. However, in biological tissue, we face the challenge here shown in this movie. Light transport transitions from the ballistic regime into the diffusive regime within a matter of a millimeter in depth. Starting with the first generation optical microscopy, which allows us to see organelles, subcellular structures, but the penetration is limited to 100 microns, which is the aberration limit, essentially one mean-free path. We stagnated at this limit for hundreds of years until modern light sources were invented, namely laser or superluminescent diodes. We were allowed to overcome the scattering problem by rejecting the scattered photons. We provide 10 times deeper penetration using confocal, for example. Now we're limited to 1 millimeter, something we call optical diffusion limit, which is one transfer mean-free path. Using photoacoustic tomography, we advance the penetration by 2 more orders of magnitude. Now we're talking about multiple centimeters penetration. We do face the next challenge, which is something we call the optical dissipation limit. We're still looking for ways to overcome the next limit. In photoacoustic tomography, we start with a nanosecond laser pulse. We broaden the laser beam such that the laser energy per area is within the ANSI safety limit. So this is a very safe technology to use. We allow photons to diffuse deeply into biological tissue. When photons get absorbed, they generate rapid heating. Every millidegree of temperature rise gives you a detectable pressure. So we can usually heat up to hundreds of milledegrees within the safety limit per laser pulse, and we get a good SNR. Unlike standard optical imaging, we receive the photoacoustic signals. Because acoustic scattering is orders of magnitude weaker than optical scattering, we can form a very sharp image by using image reconstruction. However, the contrast from light absorption, so we're combining optical contrast with ultrasonic resolution in a single image modality, where pure ultrasound imaging cannot do, or pure optical imaging cannot provide a depth. In 2003, we acquired the first functional, also the first in vivo photoacoustic tomographic images, which was demonstrated in small animals with an intact scalp and skull. This is very similar to functional MRI or bold MRI. We can see one-sided functional response to whisker stimulation. This paper has become one of the most cited in our field. In fact, since the publication of this paper in 2003, we can see exponential growth of our field. Since 2010, the Conference on Photoacoustics has become the largest at the 20,000 attendee Photonics West. Our field has been publishing over 1,000 peer-reviewed papers each year. So you can see this is a very robust field right now. More than 20 companies have been commercializing photoacoustic tomography. 3 of them received regulatory approvals for human clinical use in the past couple of years. A unique feature of photoacoustic tomography is to provide omniscale in vivo imaging from organelles all the way to small animal organisms or human organs with consistent contrast, because we always image light absorption or optical absorption as the contrast. We're plotting the image depth versus the spatial resolution. Each horizontal bar represents one of the implementations. The dashed line connects all of them. There's this scaling factor, which is the depth to axial resolution ratio, which is roughly 200. So no matter what length scale we work at, we can provide a good image to work with. This type of multi-scale imaging capability is important because in standard practice for cells and below, we use optical microscopy. For tissues and above, we switch to non-optics typically because standard optics does not provide the right depth. So we're talking about very distinct contrast mechanisms, and it's very hard to correlate information acquired across length scales. Photoacoustics can potentially allow omniscale biological research from organelles to organisms, can accelerate translation of microscopic lab discoveries to macroscopic clinical practice. For the O3 work, we used a single element transducer. It took a while to acquire a cross-sectional image because you got to rotate a transducer to mimic a ray. Finally, we built a single impulse panoramic photoacoustic CT system. The system can be configured for truncal imaging. We use the right laser, route the laser beam to a conical lens to form a hollow cone beam for maximal energy delivery to the trunk. We use a full ring ultrasonic transducer array to form a panoramic image. So we're viewing the animal from all possible angles to get the best image quality. We follow the spatial Nyquist sampling criterion, namely finer than lambda over 2, acoustic lambda over 2 in sampling spacing. We use preamplifiers to maximize the signal-to-noise ratio. We use one-to-one data acquisition, namely 512 channels of data acquisition to allow single-shot imaging for a 2D cross-section. So the data acquisition is limited by the acoustic transit time across the field of view for a small animal that's tens of microseconds. So we don't have to worry about any motion artifacts. Of course, we use a computer to form an image and display the image. Here's a close-up. This is the hollow cone beam. We have acoustic focusing in the elevational direction for elevational resolution. The XY resolution comes from the image reconstruction, which is the inverse spherical radon transform. The system can be reconfigured for brain imaging. Here we use a diffuser to form a solid cone beam to maximally deliver laser energy to the brain. And the rest of the system is very similar in operation. This is an example where we can image the whole body of a small animal. The red line shows the current cross-section being imaged. Again, each 2D image is acquired within tens of microseconds. Then we repeat the laser pulse to get different frames. So here we're repeating the laser pulses at 50 hertz. So we're getting 50 hertz frame rate. And this is faster than video rate. And you can see the close-up. We can see a lot of the internal organ structures really well without using ionizing radiation, which was required, of course, in X-ray CT, for example. And we don't have to inject any exogenous contrast agents, or in MRI, oftentimes you have to inject gadolinium. And the pharmas are interested in this type of imaging capability because you can monitor a new drug and see the response in the small animal without worrying about radiation dose, which may kill the animal, over a course of multiple months if you expose the animal multiple times. And there are many applications we can think of. And the technology has been licensed to a couple of companies. They actually acquired images even better than our lab. We scaled up the imaging system for human breast imaging. So now this system now is 22 centimeters in diameter, big enough to accommodate most breasts. Unlike standard X-ray mammography, we don't compress the breast sideways, which is painful. We slightly compress the breast against the chest wall just to stabilize the breast, to minimize motion artifact, to minimize the light delivery requirement. And we use 1064 nanometer light. This is a reasonably lower cost laser available commercially. Again, with a single laser shot, we can get a 2D cross-sectional image. Because of the bigger field of view, the image acquisition time is 150 microseconds. We ask the patient to hold her breath. Within a single breath hold, we can get a 3D image within 15 seconds. The smallest vessels we've imaged has a diameter of 1/4 of a millimeter. The one-way light penetration is about 4 centimeters. Here, this is a comparison with this FDA-approved photoacoustic images. We can get far more detail, as you can see right here. We can resolve blood vessels very well. Using the same human subject, we acquired a gadolinium contrast MRI image. So this MRI requires injection of gadolinium, which is a heavy metal, which has some known side effect. The numbered arrows point to blood vessels that are imaged by both. The lettered arrows point to blood vessels that are missed by MRI, but imaged by photoacoustics. And of course, we can see tumors in both cases. Then we developed a newer version to provide isotropic spatial resolution. There are 4 arcs. We have 1024 ultrasound transducer elements. We can rotate to form a virtual hemispherical detection array. So this has a lot of virtual detector positions. The beauty of this geometry is that now the elevational resolution is as fine as the XY resolution. The system operates in 2 modes. Then an anatomic mode takes a little longer, 10 seconds, to form a high density or high resolution 3D image. And we have a functional mode, which takes only 2 seconds. We sparsely sample the volume, and that provides a 3D image as well, but provides you functional information. We have 2 different laser wavelengths used, one to target oxyhemoglobin, the other deoxyhemoglobin. This is the first functional photoacoustic 3D image of the human brain. We started with hemianatomy human subject. When we ask the human subject to tap his fingers, you can see the brain activation. You see the detailed signal here, but you can see the color showing the brain activation. In the next slide, I'll ask our collaborator to narrate a comparison with the 7 Tesla MRI, which is the strongest field FDA allowed for human clinical use.
Here we present results from subject 1, 7T MRI on the left, functional pact on the right. Individual functions are flashed in, starting with finger tapping, lip puckering, tongue tapping, passive listening, and silent word generation. Vessels for co-registration are then labeled 1 through 4, vessel 1 and 2 being superficial temporal artery, 3 and 4 being cortical arteries. The images are overlaid, and then individual functions are flashed in, starting with finger tapping, lip puckering, tongue tapping, passive listening, and silent word generation. The vessels are again pointed out individually, vessel 1 and 2 being branches of the superficial temporal artery, 3 and 4 being cortical vessels. The lateral perturbations allow for visual spatial appreciation of the co-registration. The images are then separated, and native T1 masks are faded in. Again, 7T MRI on the left, functional pact on the right. Individual functions are then flashed in, starting with finger tapping, axial, and coronal images through the area of interest are introduced below. Next, lip puckering, tongue tapping, passive listening, and silent word generation.
So we can also build a handheld version of the probe that allows us to image different anatomical sites. This is one example where we can use it to image the neck region. One of the clinical issues we have is that we don't know how much oxygen is consumed by our brain. That's an extremely important physiological parameter, especially during surgeries. The current methods are invasive. Now, using our technique, we can measure the input to the brain, which is the carotid artery. And so we quantified oxygen saturation. And we can measure the output from the brain, which is the jugular vein. So we've imaged 7 human subjects. The average oxygen saturation is within the normal range. And so if we know both the input and the output, the difference gives us the OEF, the oxygen extraction fraction, and that allows us to indicate how much oxygen has been extracted by the brain. The other application is to detect circulating tumor cells. We know that the primary tumor may not kill the patient. It's oftentimes the metastases that are lethal. One way to generate metastasis is circulating tumor cells. And there's no non-invasive method to monitor circulating tumor cells. The standard method is to draw blood. Our body has 5,000 cc of blood. Typically, we draw 5 to 10 cc. And so you have sampling error because we only sample such a small volume. Using our technique, we can non-invasively monitor circulating tumor cells. We started with melanoma CTCs because they have melanin providing a natural contrast for us to see by optimizing the laser wavelength, and the melanin becomes very bright, as you can see right here. A melanin-containing particle, presumably circulating tumor cells, actually travel through our field of view in both cases. In this case, actually, we see a little doublet appearing several times in the field of view. And so you can imagine all sorts of applications for screening, detection, diagnosis, monitoring, therapy. Now, our field actually concluded beyond 1 millimeter depth, it was very hard to image any flow because we couldn't really resolve any heterogeneity in the blood. But it turned out that was not quite right because in venous blood, not in arterial blood, there's sufficient resolvable heterogeneity as shown in the movie right here. So now we're imaging flows beyond 1 millimeter depth. In this slide, we're going to report a newer technique where we, instead of using many ultrasound transducers working in parallel, we want to use just one. So the concept is ergodic relay. We want to use this one transducer as equivalent ultrasound array.
Photoacoustic computed tomography through an ergodic relay, or PACTOR, is an inexpensive, compact, and ultra-fast 3D imaging system. In PACTOR, photoacoustic signals generated with a single laser exposure are detected by a single-element ultrasonic transducer. The calibration is performed using a uniform absorber, such as blood. Owing to its insensitivity to the boundary conditions of the object, PACTOR requires only a single calibration for different objects. Despite the use of a single-element ultrasonic transducer, PACTOR provides effectively 6,400 virtual transducers, with each calibration pixel becoming a virtual transducer. PACTOR has been demonstrated to image hemodynamics, in vivo, in humans and animals, such as the changes in the blood vessel of a human hand. PACTOR uses one ultrasonic transducer to capture information, such as the photoacoustic signal from a blood vessel, but functions equivalently as 6,400 virtual transducers. With a single laser shot, the one-dimensional, time-resolved signal detected by the single-element transducer is acquired and decomposed to reconstruct a three-dimensional image of the blood vessel. In this work, we show that PACTOR enables single-shot, 3D, in vivo photoacoustic tomography, with an imaging speed of up to 1,000 volumes per second. These are all accomplished by a single-element ultrasonic transducer. The single detector concept in PACTOR could be generalized to other imaging technologies such as ultrasonography, sonar, and radar.
We can scale the imaging depth and spatial resolution. This is a microscopic version. This photograph shows the first 3D photoacoustic microscope. Now, this paper actually started a new field as well. Now it's becoming one of the most cited papers in our field for microscopy. So the key idea is that we focus a light beam into biological tissue. On the tissue surface, we have a donut shape. We made the core of the beam dark just to minimize the surface interference. The ultrasonic detection is confocal with light illumination to maximize the signal-to-noise ratio. With a single laser shot, we get a time of flight, a 1D image. So we're resolving the depth due to the time of flight of the ultrasonic pulse. Now, the XY resolution has two mechanisms. Within the top 1 millimeter, we can focus light, so it's optically resolved. Beyond 1 millimeter, we switch to acoustic resolution because light will diffuse. We depend on acoustic focusing to provide resolution. We raster scan this head in a water tray to get a 3D image. Let me focus on optical resolution. One of the problems we have is standard histology just takes too long. For example, for bone tissue, it takes up to 7 days to acquire image because we need to decalcify. In photoacoustic image, we don't have to decalcify. We don't even have to stain with natural contrast to get an image. So this can be done currently within 11 minutes, and we can even accelerate this a lot by using arrays. You can see how closely we can mimic standard histology using our label-free technique. And we don't even have to prepare the sample because even with a rough surface, we can scan directly. Studies have found that if we can provide intraoperative guidance for bone surgery, we can reduce the margin from 20 to 2 millimeters. So we can save a lot of healthy bone tissues, especially because bones are so hard to regrow. We can provide super resolution for the acoustic imaging by using nonlinearity. The first one shows diffraction limited resolution at 234 nanometers. Using nonlinearity, we provide photoacoustic nanoscopy at 90 nanometer resolution. This movie shows a comparison, and you can see an EM micrograph. We're looking at the mitochondria. So far, everything is light-based photoacoustic imaging. We do have a limitation, which is currently one-way penetration is about 4 centimeters. Our field has demonstrated close to 5 centimeters one-way penetration. You can provide potentially two-way light delivery, so that would double the depth, double the thickness. But we're thinking about how to extend the EM spectrum from the optical regime to the radio frequency or micro regime for even greater penetration. And so the precursor is a ultrasound CT system. It turned out this is the first whole body ultrasound CT system ever built. And so we have a 60 centimeter diameter, essentially a water tank for acoustic coupling. And we rotate the system to acquire sufficient data for ultrasound CT. And this is one of the first images required in vivo. In humans, we can identify internal organs quite well using the system. We can also potentially use this to guide needle biopsy. And so this is a demonstration. You can see the needle tip because we have acoustic emission from the needle tip. We can track the system as we poke the needle, and we can follow the tip. And we use a circle to highlight where the tip is. Again, you can think of all sorts of applications for robotic surgery or even for a real person surgery. Now, so far, everything is sonic speed imaging. Can we provide light speed imaging? It turned out we could. So we built compressed ultra-fast photography at 100 billion frames per second. And so we've actually increased the speed by 3 orders of magnitude now. And we're still the fastest camera in the world in terms of real-time imaging. And so at this kind of frame rate, finally, we're able to see a light pulse in real time with a single laser shot. You don't have to repeat the laser pulse. You can see this light pulse traveling, getting reflected, refracted. You have 2 light pulses in different media. And we can provide single shot fluorescence lifetime imaging. And so we use 2 channels. we switch the camera to 2 color channels, 1 color for excitation, 1 for emission. The green channel, which we'll show later, shows the excitation pulse. And then the red channel shows the detection. So again, you can imagine all sorts of applications, such as a single shot flame version. There are many applications. Some are in physics. For example, can we use this single shot technique to image events that are not repeatable, chaotic events? And so this is a real-time imaging of a bouncing photon packet in a chaotic cavity. We had 2 takes. If you overlay the 2 takes, you'll see that at early times, the 2 pulses are overlaid. They travel together, but eventually they'll split. And we can also study the transition in real time between a stable cavity and a chaotic cavity. And there's a Kerr gate, which is light speed. You can switch that gate on and off. You allow the light pulse to cross into the chaotic cavity. There are also biomedical applications. This is a phase contrast imaging using our fast camera of axon, myelinated axons. So we're sending an artificial, very short electric pulse into the axon. We can monitor the propagation of the signal right here. And so as we know, between the 2 nodes of our NVA, the electrical signal is essentially the highest speed that you can achieve for a neural signal propagation. So we're able to measure that speed at about 100 meters per second. Now you can imagine down the road, if we can develop a imaging or apply this imaging technique for a neural network, can we study brain function using this phase contrast ultra-fast imaging technique? And so that would be extremely exciting because, can we tease out ultimately the functions in the brain? Now, so far, everything is classical. Can we leverage some quantum resources for quantum imaging? And let me talk about the standard quantum limit versus the Heisenberg limit using n photons. The spatial resolution at the standard quantum limit scales with √n. The standard limit is achieved with a regular light source. Even a laser is considered a regular light source. Examples include 2-photon microscopy or Palm storm. In 2-photon excitation, you got 2 photons which do not need to be correlated or entangled. You go through a virtual state, so you have this double photon excitation. From the intuitive perspective, n statistically independent photons average the spatial standard error down by √n, according to the central limit theorem. Now, what's exciting is in the Heisenberg limit, the spatial resolution scales more efficiently with n directly. The Heisenberg limit is achieved with an entangled photon source, such as a SPDC source. Now, intuitively, any entangled photons behave like 1, but with n times greater momentum, therefore, n times shorter the Broglie wavelength. So that means you can achieve a much finer spatial resolution. And so we've demonstrated with n of 2, very interestingly, even when the 2 photons from an entangled photon pair are spatially separated, so we call that signal and idler photons, only the signal photon sees the object. But we use coincidence detection to detect the entangled photon pairs. We can achieve a factor of 2 enhancement in spatial resolution, as demonstrated in this slide. So in the same system, we use the classical channel to acquire image, and you can see the improvement in spatial resolution in the quantum approach. Let me thank Caltech for building me a dream lab. This photograph shows one of the floors of our lab. We have openings for graduate students and postdocs. Credit goes to lab members. We have funding from NIH, NSF, and CZI. There are a couple books. If you're interested in greater details about our work, you can refer to them. Thank you very much. I'll be happy to entertain any questions.
Thank you very much for your nice talk. So now
Thank you.
it's open for questions. So you can write in the chat, or you can just directly also speak. Maybe I start with a very general question, is that when you use photoacoustic to image as a diagnosis, does the acoustic wave itself influence on the function of the inside the body with the biological parts? So will that anyhow somehow hamper?
It should be extremely weak. It's not detectable because we're following the ANSI safety limit.
Okay.
And so for each laser pulse, you're using 20 millijoules in the visible spectral range. The safety limit is 20 millijoules per centimeter squared. If you expose the tissue for over 10 seconds, you also have to make sure the average power per area is within the safety limit, which is about 200 milliwatts per centimeter squared. And so this is essentially comparable to the sunlight you get, on the Earth's surface. We actually don't use the UV, right? Because when you're exposed to sunlight, you're also exposed to UV and short wavelengths. We typically use a longer wavelength. And so shorter wavelengths, light is much more strongly absorbed.
Yeah, thank you.
So,
Thank you very
so
much.
you actually feel more heat under the sun than under our light exposure. Under our light exposure, oftentimes you don't feel anything.
Yeah.
So it's extremely weak, but you cannot tell people there's no effect, right? Because we're exposed to the sunlight, we have some effect. But if there's any effect, we have not observed anything yet. So it's going to be nearly none.
So is there any further questions?
I'd like to ask a question.
Yes, please.
Thank you very much for very interesting talk. And concerning the entangled photon usage, in case you generate photons, entangled photon from 2 omega photon to 1 omega, 1 omega. In that case, then the resolution is not enhanced because of the 2 omega can have resolved corresponding to the half lambda of the one entangled photon can resolve. So there is no gain in resolution.
Very good question. Very good question. So the question is that in two photon microscopy, if you address the same excitation level, right? So you use 2 photons, then you have to use a longer wavelength to begin with. So you got a bigger diffraction to begin with. And so that's why for 2 photon microscopy, your resolution is actually worse by roughly square root of 2, right? Relative to, for example, single photon confocal imaging. However, for the quantum version we discussed, so when I mentioned the resolution enhancement is assuming you use the same wavelength, right? So for the quantum version, if we don't want to expose UV light to biological tissue, which is harmful, right? So we can send in 400 nanometer single photon light to the tissue, but we get the resolution of 200 nanometer, if that makes sense.
Yeah, I understand. So just the case of UV excitation, then the photo damage becomes a problem. But in case of entangled photon, even though the resolution enhancement cannot be obtained, but still it is safer, is the point.
Yeah, that's right. So so that's an important point for biological applications. You can get a benefit of the 200 nanometer light without causing tissue damage, right? So that's one aspect. The other aspect is I wrote the number n here. Right now n is 2, but from the physics perspective, 2 is not the limit for n. So what we are most excited about is the potential of getting a bigger n. If one day N is big enough, then we can potentially provide, in the wildest dream, right, the EM resolution using photons. And that would be extremely exciting. I still hope that one day we can see that.
So you're thinking, for example, the infrared or near infrared or mid infrared?
Well, you can use, even visible photons, right? But if you entangle, for example, 100 photons, then the de Broglie wavelength is going to be 100 times shorter. Right.
That is in either case, but entangled photons are very fragile, easily, even if any small loss, then the entanglement is destroyed easily. So 100 entanglement is very extremely difficult.
Yeah, that's a very good question. Let me so in order to go back to the slide here, so let me show you the setup. Now you can imagine down the road if we can develop. So it's here. All right, I have to reshare the screen, looks like. So in this setup, you can see here, only the signal photon goes through the object. All right. I mean, you can image the cells. And so the isolated photon does not go through the object. Let's not, be too ambitious. You want to image a thick tissue, for example. I mean, then scattering would ruin your entanglement. All right. So in this case, the entanglement is maintained between the two photons, even after you go through the object. And that's why we can detect the coincidence counts. And that gives us the resolution. And this is only for N of 2. But, if you can scale N of 3, you got 3 photons, that would be the simplest extrapolation, of course. So this object is not going to provide, bigger problem than the N of 2 version, if that makes sense. So even though entanglement is fragile, it's equally fragile here, that you can still capture those photons that maintain the entanglement. So you achieve the benefit of a shorter de Broglie wavelength.
Yeah, but in case of 3 photons, then the 3 photon entanglement is difficult to generate. Just
very difficult to generate.
Parametric conversion. It must be cascading parametric down conversion is needed, and that is even each step the efficiency is very poor. So it's very challenging and very interesting, but
no doubt
it is very difficult.
No doubt, it's an extremely challenging direction.
Yeah,
but the physics cannot rule out the possibility.
Yes.
Yeah. So we realize that it's not an easy task. So you're right.
In any case, your challenge is very. I'm expecting to hear your success in future.
Thank you. Yeah, it's actually extremely intellectually stimulating to work on this type of problems, but
yes,
there are a lot of challenges for sure.
Thank you very much.
Sure.